Every spark, spill, and reaction we see on a job site starts with one thing: chemistry. You don't have to be a scientist to understand it. You just have to see how molecules behave in the real world. In this video, we'll connect the dots between what's in your safety data sheet and what actually happens in the field. Because when you understand chemistry, you can predict risk and prevent it. We'll cover what every OHST candidate and safety professional should know: how acids, bases, solvents, and gases behave in the environments we protect. You'll learn why pH matters for corrosion, how fire chemistry explains ignition, and how understanding reactions can make you faster at spotting hazards before they happen. Let's break down chemistry into what it really is: the science of safety. Temperature defines how matter behaves. Celsius and Fahrenheit measure relative heat, while Kelvin measures absolute temperature. Essential for chemical calculations like gas laws. Understanding these scales helps predict expansion, reactivity, and safe working conditions. You might see Celsius in lab data and Fahrenheit in field readings, so know how to switch between them. Fahrenheit equals 9/5 times your Celsius plus 32. Celsius equals your Fahrenheit minus 32 times 5/9. Kelvin equals your Celsius plus 273.15. In OHST exams, these conversions often appear in questions about exposure, evaporation, or gas expansion. The periodic table isn't just for chemists, it's a safety map. Each element's position predicts how it reacts, corrodes, or combines. Metals, gases, and reactive families all behave according to their place on this chart. Columns or groups share outer electron behavior. That's why group 1 metals react violently with water. Rows or periods show energy levels. Recognizing these patterns help predict compatibility and reaction hazards. Across a period, atoms shrink and electronegativity increases, meaning atoms pull harder on the electrons. Down a group, atoms get larger and easier to ionize. These trends affect corrosion, bonding, and conductivity. This is critical in material selection and hazard control. Each element box tells a story. The number on top is the atomic number. How many protons? The big letter is the chemical symbol. The number below gives atomic weight. For example, hydrogen symbol is H. The atomic number is 1. It's the simplest and most reactive gas. Chemical equations describe what's happening when substances react. Reactants go on the left, products on the right, separated by an arrow. Subscripts show the state: solid, liquid, or gas, or aqueous. Coefficients tell how many units react. Balanced equations follow the law of conservation of mass. Atoms aren't lost or created, only rearranged. Balance by adjusting coefficients until each element count matches on both sides. OHST exams often test this with simple combustion or synthesis reactions. A solution is a uniform mixture, a solute dissolved in a solvent. In the field, think salt in water or coolant additives. The interaction between solvent and solute determines stability and concentration. It's key for safe mixing and disposal. Percent concentration shows how much solute is present. You'll see it as percent weight over volume, milligrams per 100 milliliters, or parts per million. For exposure or dilution questions, remember percent equals solute divided by solution times 100. High concentration means higher risk. Always label and handle accordingly. For the OHST exam, focus on conversions, periodic trends, reaction symbols, balancing basics, and concentration math. Chemistry and safety isn't about memorizing, it's about recognizing patterns and applying them to real-world scenarios. Keep your notes handy and remember every reaction tells a safety story. Molarity, that's your measure of how concentrated a solution is. 1 molar equals 1 mole of solute in 1 liter of solution. Think of it as the strength of your mix, like how sweet your coffee gets the more sugar you add. 1 mole equals 6.022 times 10 to the 23rd particles. That's Avogadro's number. It's how we connect atoms you can't see with grams you can weigh. 1 mole of carbon weighs 12 grams. That's your conversion bridge between micro and macro. Dilute means weak, more water, less solute. Concentrated means strong, less water, more solute. A saline solution or syrup shows how concentration changes flavor, density, and even boiling point. Solutions stay mixed. They don't settle. They don't scatter light. Add salt and water's boiling point climbs while its freezing point drops. That's why we salt icy roads. Chemistry at work. Warm water dissolves solids faster, but gases, they bail out. That's why your soda goes flat faster in the sun. Pressure keeps gases dissolved, which is how seltzer stays fizzy. So yeah, your soda's not broken, it's just warm chemistry. Like dissolves like. Polar dissolves polar. That's water and salt. Nonpolar dissolves nonpolar. That's oil and grease. And that's exactly why oil and water just don't mix. When atoms break old bonds and form new ones, that's a chemical reaction. It might release heat, light, or just rust on your truck. From welding to wastewater treatment, reactions rule your workday. Heat it up and everything speeds up. Every 10 degrees Celsius, most reactions double in speed. That's why food spoils faster in the summer. Molecules are partying harder. Catalysts make reactions go faster without burning out themselves. They lower the energy needed to get things moving, like giving molecules a shorter hill to climb. Combination, 2 become 1, like hydrogen and oxygen making water. Decomposition, 1 breaks into 2, like water turning back into gas. Think of it as chemistry's remix. In a single swap, 1 element kicks another out, like copper stealing silver's seat in silver nitrate. In a double swap, 2 compounds trade partners. Think of it as chemical speed dating. Covalent bonds share electrons. Think teamwork. Ionic bonds transfer electrons. Think trade. Covalent is like holding hands. Ionic is like giving up an electron handshake. Hydrogen bonds are quiet heroes. They're weak alone but powerful together. They make water sticky, ice float, and DNA hold its shape. These are the subtle forces between molecules. Dipole, dispersion, and hydrogen bonding. They're why wax feels solid and alcohol evaporates fast. When electrons move, chemistry happens. Oxidation means loss. Reduction means gain. Remember OIL and RIG. Rusting, combustion, batteries, all redox in action. Every corrosion, every soap bubble, every sour taste. Chemistry explains it through oxidation and pH. Oxidation state and oxidation number, 2 names for one idea. How many electrons an atom has lost, gained, or shared. When iron rusts, when copper tarnishes, it's oxidation state that tells the story. Tracking these numbers, let us follow electrons like footprints through every reaction. Oxidation numbers aren't just theory, they're the keys to balancing redox reactions. Every atom's number tracks how electrons move. Oxidation is loss, reduction is gain, but the total electron count must always balance. Once you assign numbers correctly, you can balance any redox equation like a pro. Let's walk through how oxidation and reduction really works in a chemical reaction. We'll use iron and dichromate, a classic redox pair. Remember, oxidation means losing electrons and reduction means gaining them. We'll assign oxidation numbers, track electron changes, and balance the entire equation. Step 1. Write the two half reactions. First, separate the overall reaction into the oxidation and reduction half reactions. Step 2. Balance atoms in each half reaction. On the oxidation half reaction, all we have is iron, and there's one iron on each side, so it's already balanced. But on the reduction half reaction side, balance the metal atoms first. There are two chromium atoms on the left and one on the right. So we add a coefficient of 2 to the chromium 3+. Balance the oxygen atoms by adding water molecules, H2O. There are 7 oxygen atoms on the left, so add 7 water molecules to the right. Balance the hydrogen atoms by adding hydrogen ions. There are 14 hydrogen atoms on the right from the 7 water molecules that we added. So add 14 hydrogen ions to the left. Step 3. Balance the charge in each half reaction by adding electrons. On the oxidation half reaction, your reactants are iron, and the charge is 2+. On the products, the charge is iron with a 3+. To balance the charge, add 1 electron to the right side. On the reduction half reaction, your reactants, the charge is 14 times +1 plus 1 times -2 equals a +12. On the products, your charge is 2 times +3 plus 7 times 0 equals a +6. To balance the charge, add 6 electrons to the left side. Step 4. Equalize the number of electrons lost and gained. The number of electrons lost in the oxidation half reaction side must equal the number of electrons gained in the reduction half reaction side. On the oxidation, 1 electron is lost. On the reduction side, 6 electrons are gained. Multiply the oxidation half reaction by 6 so that both half reactions have 6 electrons. Step 5. Add the half reactions and cancel out common species. Combine the two half reactions and cancel any species like electrons that appear on both sides of the equation. And step 6, your final check. Confirm that the atoms and charges are balanced on both sides. As far as your atoms, we have iron 6 on the left and 6 on the right. We're balanced. For chromium, we have 2 on the left and 2 on the right, so we're balanced. For hydrogen, we have 14 on the left, 7 times 2 equals 14 on the right, balanced. For oxygen, there are 7 on the left, and 7 times 1 equals 7 on the right, so we're balanced. For the charges, the left side, we have 6 times a +2 plus 14 times a +1 plus 1 times a -2. So 12 plus 14 minus 2 gives you 24. On the right side, we have 6 times a +3 plus 2 times a +3 plus 7 times 0. This gives you 18 plus 6 plus 0, which gives you a +24. The charge is now balanced. And here's your final balanced redox equation. Acids are the proton givers, the tang of lemon juice, the sting of battery acid. In water, they split, releasing hydrogen ions that make litmus paper blush red. Strong acids like hydrochloric acid and sulfuric acid ionize completely. Weak acids hold back a few protons. Either way, acids drive corrosion, digestion, and industry. Bases are the proton takers, the slippery feel of soap, the bite of ammonia. Drop them in water and they pull in hydrogen ions, turning litmus paper blue. Strong bases like sodium hydroxide and potassium hydroxide strip protons fast. Weak ones barely make a dent. Together with acids, they keep chemistry and our blood balanced. pH measures the power of hydrogen, the heartbeat of every solution. A low pH means high acid strength. High pH means a strong base. Water sits neutral at 7, stomach acid at 1, bleach around 12, and our bodies, lakes, and oceans live within narrow pH windows that control life itself. From nuclear reactions that power the sun to the biochemical processes that power your body, every safety professional should understand the science that keeps both running smoothly. Let's connect chemistry to real-world safety. Nuclear reactions happen in the atom's core, releasing huge amounts of energy. Unlike chemical reactions that rearrange electrons, these split or fuse nuclei. The result? Radiation, heat, and new elements. Half-life is how long it takes half of a radioactive sample to decay. Understanding decay helps in nuclear safety, medical imaging, and environmental monitoring, all relevant to safety science. Atoms of the same element can differ in neutrons. Stable isotopes last forever. Unstable ones decay and emit radiation. Carbon-14 dating or nuclear monitoring all depend on isotope science. Alpha particles are heavy and stop at your skin. Beta can pass through paper but not metal. Gamma rays, they're the most penetrating, used in power, medicine, and safety monitoring. Biochemistry connects chemistry to life, from glucose in your blood to the energy in ATP that fuels every muscle. These processes drive metabolism, safety psychology, and health monitoring. Carbohydrates are your energy source, sugars and starches that break down into glucose. Through glycolysis, glucose becomes pyruvate and releases ATP, the energy currency of life. Proteins build and repair lipids, store energy, and nucleic acids store genetic information. Together they maintain cellular balance, a concept crucial in industrial hygiene and biological monitoring. From radiation exposure to metabolic stress, understanding chemistry helps us control hazards, analyze samples, and interpret data in the OHST field. Chemistry isn't just formulas, it's the foundation of every safety principle we apply. Understanding reactions, radiation, and biological processes empowers safer work environments. Join me next time as we shift from molecules to math in our next video, Business Calculations and Analysis Made Simple.